Okay, we're going to be taking a look at Boyle's law and how to calculate these gas law problems. Now, one thing I'd like to ask you to do when you're ever doing these problems, pause during the video and try them out on your own. Don't just watch the video. Of course, it'll make sense then. You've got to struggle through them and try to figure them out on your own. So to figure out Boyle's law, first of all, it is P1V1 equals P2V2. And we're always looking at the situation before and after. So we're taking a gas and we're changing something about it and seeing how it behaves. Now, I will say with this first one, there's a couple of curveballs on this because it talks about standard temperature and pressure. And I should say the STP, whenever we mention that, that means that we're dealing with 1 atmosphere of pressure and we're dealing with 273 Kelvin. Now let's go ahead and continue on to the problem. So step 1, I always like to take some time to write down the formula. P1V1 equals P2V2. And in this problem, originally, what is it at? Well, we had a liter of gas at this, and then it's compressed. So originally, it was at that standard pressure, which was 1 atm. So in that same place where the P1 goes, I'm going to do my second step. I'm going to put in 1 atm. And then in the spot for the volume, what was the volume originally? It was 1 liter. And then I put equals. What is the pressure afterwards? Well, that's what we don't know, P2. That's what we're trying to figure out. I do know that the volume afterwards is 473, and oh no, another curveball. This is liters, this is milliliters. We cannot have those two hanging out on this opposite sides of the equation. This has to change for liters. Many of you have done this. If you haven't, though, you're just going to have to move the decimal 3 to the left. 473 milliliters is really 0.473 liters. Now, once I've got that, I've got to solve for P. So I'm going to divide by 0.473 liters and divide by 0.473 liters. These two cancel. I'm going to go ahead and do my math on here, and I get 2.11 atm for my first answer. Next one, we got a bomb, okay? And there's gas inside the bomb, but it only takes up a teeny tiny amount of space. And that gas inside the bomb is under an enormous amount of pressure. Again, pause this, try it out on your own. Now, when it explodes, that little bit of gas that's under a lot of pressure is now going to be under just regular old standard pressure of 1 atmosphere. So what's going to happen to that air? That air is going to expand. It's going to take up tons of space now. So let's go ahead and figure out what it would be. So I'm going to write it like this time. I want to write right underneath it. So I want to think about, okay, what am I going to do for P1? My initial pressure, well, that's that big number, 4.0 times 10 to the 6 atm. What's my initial volume? Well, the initial volume, that was 0.050 liters. And then afterwards, the pressure, the new pressure is going to be 1.00 atmospheres. And the new volume, I don't know the new volume. That's what I'm trying to figure out. So to figure this out, I've got to divide both sides by 1, which we know that's not going to change anything. Divided by 1 atmosphere. And now these will cancel out. I'm going to take, I should have mentioned this on the top one. When you're doing these problems, I like to take this first number, 4 times 10 to the 6 times 0.050, and I like to press equals. Then I divide it by the 1, equals. Sometimes your order of operations, your dear Aunt Sally will come out and beat you up if you do things wrong. When I go through all of this, I'm going to get an answer of 200,000 liters, but I got a problem because I need 2 sig figs, 2, I need 2. So to make this to be 2 sig figs, I could do that, or I could do 2.0 times 10 to the 5. 2.0 times 10 to the 5th liters. That works as well. Number 3. Okay, I've got some gas, 2.0 liters of gas at 1 atmosphere. I compress it to I compress it with a lot of pressure. What would the volume of the gas be? Well, the gas is going to get really small. How small? Let's go ahead and figure it out. The original pressure, P1, that's 1 atmosphere. The original volume, that's 2 liters. And afterwards, it's at this new pressure, P2. That's at 6.00 times 10 to the 4th atm. And we're going to have a new volume. So I'm going to divide. I need to get rid of this number. I need the V2 by itself now. So I'm going to go 6 times 10 to the 4th over here. I'm going to go over this side. 6 times 10 to the 4th over here. These two are going to cancel. My V2 is going to equal all that stuff there. So I'm going to put that into my calculator, and I'm going to get 3.33 times 10 to the negative fifth. Now, we were solving for volume, so that's going to be, well, this was liters, so the new answer will be in liters. And 3 sig figs, 3 sig figs, 3 sig figs. I already have 3 sig figs, so I'm good. Number 4, I'm going to Mount Everest. That's a bad idea. That's really dangerous up there. You should not do it. Now, if you do that, it's going to be really low pressure up there, which is why you bring oxygen tanks. Now, this tank is 10 liters, so I mean, think about a 2 liter. You know what one of those looks like, 5 of those. There's your tank, and that air inside of there has a pressure, really a big pressure of this. But what about when I get to the top and I open up that valve and let the gas out? Well, now it will be under this pressure. So this is my initial, and my initial, this is my final. So I'm going to go ahead and do my initial 3.04 times 10 to the fourth millimeters of mercury. Now that is a different unit for pressure. That's okay. That's all right. Because I have the same different unit on both sides of the equal sign. Times the volume, which is 10.0 liters. Now equals, what's the new pressure? The new pressure is 150 millimeters of mercury times the new volume. So basically I've got a whole bunch of gas, 10 liters of it, squished. I'm going to go to the top of Mount Everest, unsquish it with less pressure, and see how much space that gas takes up. So I'm going to divide this by 150 millimeters of mercury. Divide this by 150 millimeters of mercury. And when I do this, I'm going to get an answer of 2026.67. That's going to be now liters. Sig figs 2, 3, 3. I'm going to do, oh man, a weird one again, because 2 sig figs, I'm going to get 2,000 liters, or I'm going to get 2.0 times 10 to the third liters. Either one of those is fine. Next one, submarines. They got to be really strong, okay? We got a small submarine, 15,000 liters of space, and it's got a pressure of 1.2 atmosphere. Now, it's going to be at the bottom of the ocean. It's going to break. This is not a good thing. Now, the bubble of air that was inside of it was that size. Is going to be squished now by 250 atmospheres of pressure. So this is the before stuff, and this is the after stuff. What's going to happen to that bubble of air? So beforehand, it's 1.2 atmospheres, and beforehand, it's 15,000 liters. Afterwards, it's going to be experiencing 250 atmospheres. Okay, so how big is the air bubble going to be? Let's find out. I'm going to divide this side by 250 atmospheres. I'm going to divide this side by 250 atmospheres. And when I do this, I'm going to find out that the new pressure is going to be 72 liters. That's really bad, okay, because it was this big and now it's this big. It just got squished, okay? Not a good thing to happen. And 2 sig figs would be correct. Last but not least, we've got divers getting the bends. This is not good. You've got bubbles in your blood. And when you go down deep underwater, those bubbles get squished, and you've got lots of bubbles in there. And you've got this many bubbles, this volume of bubbles in your blood, where you're experiencing tons of pressure. But then you decide, hey, I'm going to swim to the surface, or close to the surface. And as you swim up, you have less pressure. What's that new volume of the gas? What's the gas going to do? So initially I have 250 atmospheres of pressure. Now remember, we're doing all this based on P1 V1 equals P2 V2. So this is my P1, initial pressure. Initial volume is 0.050 liters. Afterwards, what's the final temperature? Well, when I swim up towards the surface, I have less pressure now, 50.0 atmospheres. And what's the new volume? Well, we don't know the new volume, V2. So now I can go ahead and divide by 50.0 ATM and divide this side by 50.0 ATM. Cancel, cancel. I can find out that the new volume of those bubbles is going to be 0.25 liters. With sig figs, that actually converts to 0.3 liters. And the question says, do you think this will harm the diver? Well, if you had a teeny amount of bubbles in your blood, and now all of a sudden it's gone from 0.05 to 0.3, that's a big problem. You've got too many bubbles in your blood, which can actually lead to paralysis or even death. And that's all due to air pressure, or pressure in general.